Hi, everybody. So, we are getting into inferential statistics, and this is now, I don't remember how many videos I've made trying to make this to work. Um, it just, it's just taking time, and I keep catching little glitches as we're going. So, all right, the idea behind inferential statistics is we recognize that sampling is very challenging. We can't often get a whole grip on the population. Running one, maybe two samples is all we can afford to do. So we often use a computer model like this Jamovi that we have here to try and do a thing called bootstrap resampling or permutation resampling. So bootstrap is when you pull something out and then you place it back in. And then permutation resampling is you pull it out and set it aside. When we're doing the confidence interval stuff in a minute, we're going to be doing bootstrapping, and just keep that in mind. All right. A confidence interval is not a probability. This is where we're talking right here. It's not a probability. If we have the 95% confidence interval, or we're trying to find that, basically it's an interval. And the formula for the interval is x bar or p hat. It's the sample value plus or minus. They're both plus or minus, and you get this thing called a multiplier. And in the world of sampling, typically you use a thing called the t-distribution. Sometimes, or sampling for means, it's the t-distribution. And in the proportion world, it's the z-distribution. And then it's the sample standard deviation divided by the square root of the sample size. And in this one, it's the square root of p hat q hat divided by n. Just a couple of comments here. Confidence intervals and hypothesis tests they work together. Your hypothesis test is a process, and it's a process to be followed. Let me just point out that these values we'll learn how to find later. These values we'll learn how to find. I'm just quickly showing you the formula. And what I'm trying to do is develop a sense as to how it works. Not in terms of the formula yet. That we'll get to later. All right, so briefly, if you're dealing with the 95% confidence interval and you're dealing with a two-tailed hypothesis test, they fit together nicely. So the 95% is in the middle, and then the 5% gets shared in the two tails. And I didn't say this, but the hypothesis test process requires that it's built off of a thing called the level of significance, or alpha. And your alpha, if it's a two-tailed test, gets shared between the two tails. Your confidence level, the 95% confidence level, sits in the middle. If it's a one-tailed test, this alpha gets just placed in one tail. And then this piece here has to be equidistant and with this piece there. And so if that's 5%, it's like thinking about 5% being over on the other side, and so there's a 90% confidence interval in the middle. So there's a connection between hypothesis testing and confidence intervals, but it's not perfect all the time. If it's the two-tailed test, then the confidence level and the two-tailed test add up to 1. All right. So basically what I'm trying to get at here is this is a range. And that range works this way. So if you do 100 confidence intervals, and it's a 95% confidence interval that you're working with, about 95 of them will have the population parameter. It could be 90, it could be 98, it could be 89, but it's about 95. All right. So let me do the following. We're going to try and discover or make a statistical argument that goes, suppose you have a 30-question true-false test. Would a class average percentage of 80% convince you that the class studied? All right. So let me travel here, and I am going to click on single proportion confidence interval. And I'm going to put A in the variable spot, and if we look at this, we've got 15 corrects and 15 incorrects. Show you the data. All I did was I just put, all right, so if they were guessing, somewhere around half of them would be correct, and about half of them would be incorrect. So I have corrects and incorrects, okay? So what's going on here is that um, we are bootstrapping this set of proportion or set of values here, not values, these uh, yeah, the confidence and the I'm sorry, the correct and incorrects. And every time we pull out a correct, it writes down correct and it pops it back in. And then every time it pulls out an incorrect, it writes it down and it pops it back in. And we're going to get the proportion of corrects and the proportion of incorrects. It's not perfect. It won't be zero point 0.5 each time. And in fact, we have like 0.525 and 0.55 and that kind of thing. So it works out that all of the possible things that we look at, if we did 100 reps of doing that bootstrapping, our proportion distribution is going to look like this. And in fact, our confidence interval is going to go from zero point 0.6 repeating to 0.33 about. And what it's done is that it's taken all of these proportion values and it's basically done this formula. And it said, oh, we're about here to here. But simply put, if we count how many are here out of the 100, we're going to see 95 of them. And then we're going to see 5 of them about out in the extreme. So we build this sort of 95 setup, and the other 5 are out in the tails. Now, don't get hung up on that at the moment, but if you look for this 0.80, well, the extreme values are just a bit beyond 0.70. Here's your 0.75, but there aren't any values out at 0.0 or 0.80. And these are all built on guesses. People were guessing. So it's probably a pretty good indication that we're having individuals that are studying. Okay? Now, let me do a hypothesis test type of scenario, and I'll go back to analysis. We'll go back to randomize. We're going to do single proportion hypothesis test. Now, here's where I keep getting like sort of stopped up. So we are going to put in our variable. Now, wrong thing to click. Okay, so this is all of the data if we were guessing, right? All right. Now, let me get back over here. Back over here to the hypothesis. All right. Now, we're trying to see if we are at 50%, which is guessing, or if we have something different. Okay. Now, our data is the 50%. What we need is our data to be an 80% scenario. Okay. So I need to go back to our data and I need to go and say, all right, what will it look like if our, not our data, our analysis, what would it look like if we did an 80% and everybody actually had performed and had studied and our p hat would have been 80%. So I'm going to put in 0.80. I'm going to turn in, and I'm assuming that this would be an indication of people studying, okay? And if they weren't studying, it would be a less than, okay? So their score would be less than. So I'm going to pop in the A, and you'll notice that our person who, where did it go? Whoops. notice that our person, or the idea of, oh, I've got 50% going on. Here's our observed proportion of 50%. Well, these are our sample results if we had a group that studied and our 80%, whoops, that's got to be 0.8. So if our proportion or our percentage average was 80%, these are the guessers. That's the person that guessed. That would be 50%. These are the results that we had that individual studied. Now look, the center is around the 80, and then if you look here, you're going to get some people that even though they studied, they didn't perform terribly well on the test. You're going to have some people that studied and they performed very well on the test, but there's not a bunch of them. Most of the individuals land around that middle. And so what this is indicating is that probably people studied. Okay, so we used the idea from the data that, okay, this is what it would look like if people were just guessing. And then we create a hypothesis test and we generate a distribution based off that hypothesis test, and we say, oh, look, this is what guessing looks like. If they were just guessing, they would have landed here or below. Everybody was studying, most likely. You can do the same idea if you had 30 questions and you had 5 A, B, C, D, E. So what would happen is you'd have corrects 1/5 of the time, and so you would repeat that process. So you'd have 1/5. 1/5 of 30 is 6. So you'd have corrects here, and then everything else would be incorrects. And so when we're dealing with that hypothesis test, and did I say 80 again? 30 questions. Can you tell if a class as a whole studied? Again, we'd use 80. I didn't put 80 in there, but just pretend we did 80. Well, look, if they're just guessing, about 20% of the time, they're going to be correct, and the rest of the time, they're not. Well, these individuals studied because their average is higher. Now we could do the confidence interval as well. I'll do that just briefly. Randomized confidence interval. We'll pop that in. Now, our class average was 80%. This is built off of, this is built off of the idea of guessing. Well, with the guessing, somebody actually got up to about 36%, somewhere in that vicinity. The confidence interval is between 0.066 and 0.36. And if people are getting 80%, they are definitely studying. There's no indication of individuals being way up in that level based on the proportion that's going on. All right, I'm going to pause, or actually I'm going to stop there. And all I'm trying to do with this video is give you an indication of how statistics kind of works in terms of inferential statistics. It's not a brilliant video, I recognize that, but we use this idea of if it's very different from the distribution, then there's something statistically significant going on, and we can base decisions off of that. Okay, I hope that helps. You guys have a good one.